wabarakatuh. So we continue with chapter number 11, ion and counter ion. Okay, so these are for part number 1. Okay, so what is the ion and counter ion? So the biological environment is a salty aqueous solution. Okay, so we have in our blood, okay, in our uh, cell solution is a salty aqueous solution. Okay, so the ion dissolved in water are pushed and pulled by the electrical force from other ion and charged micromolecule. Okay, so there will be an interaction, repulsion, attraction from other ion or molecule. Okay, and charged molecule tend to be surrounded by ion of the opposite sign. So if charged molecule is negative, then positive ion will populate it, uh, cover it, this charged molecule. Okay, and this surrounding ion neutralize electrostatic interaction and screen them out. Okay, so if the ion is the opposite ion is all over the charged molecule, then if let's say if another charged molecule coming to this charged molecule, then that charged molecule will not sense the existing of this charged molecule. Okay, so it will come closer and closer to this charged molecule. Okay, so this one contohnya macam kalau contohnya presiden, kalau dalam kitanya presiden, okay, so dikelilingi oleh secret service ke, okay, so we cannot sense the existence of the president, ataupun kita tak dapat merasa aura presiden tu. Okay, okay, and dissolved ion we alter the energetic landscape in a solution. Okay, so this one will this dissolved ion will change the energy, the repulsion on the attraction energy of the solution. Okay, so these are the example for Na plus and Cl minus. So attraction force minus 9.3 times 10 to the power minus 14 argon when the two ion is in direct contact. So these are the by using the Coulomb potential. So R is 3 Armstrong, var epsilon dielectric constant is over 3 is 80. So we get this equation. And for the thermal fluctuation, this one is because of the temperature. So kBT equal to 4.1 times 10 to the power minus 14 argon. So here we can say that this U is greater than the Coulomb potential is greater than the thermal fluctuation. So the Na plus Cl minus is still intact and not separated. So meaning that even though they dissolve in the water, but they are still near each other. So but here minus 9.3 times 10 minus 14 is for weak to cause the stable solution. So they dissociate and dissolve in water. Okay. So electrostatic interaction, a long range interaction. So for Coulomb potential, it decreases slowly with the increasing R. Okay, so this one we know that if we increase R, U decrease. Okay, and special distribution of Na plus and Cl minus spend more time in each other vicinity. Okay, so meaning that macam saya kata tadi, dia masih ada, walaupun dia dissolve dalam water, dalam air, tapi dia masih berada berdekatan antara satu sama lain. Okay, so we see this other Poisson equation from our PDA. Okay, but here we use this Poisson equation as the relation between the electrical potential and the charge distribution. Okay, so if this charge distribution will affect this electrical potential. Okay, so we have this equation. Okay, so from your PDA, maybe you can see another example. Okay, so this one is generalized Coulomb potential for an arbitrary distribution of charge. So we want to see whether kalau banyak charge dalam the solution, what will happen for the Coulomb potential. So R is the position with respect to some charged object of interest, which could be an ion, a charged protein, a membrane, or a biopolymer. Okay, so if we have a charged protein, so let what happen uh, for the ion that is R1 distant from this charged protein, and what are the Coulomb potential of the, let's say, B ion that is R2 length or distance from this charged protein. Okay, so the geometry will determine the coordinate system. Okay, so whether Cartesian, the spherical, the cylindrical system, so we can modify this or use this one. Okay, so here is for a simple binary sat, Na plus Cl minus, so the charge density is equal to the charge density rho E equal to E times A tilde 10 to the power minus 3 C plus R minus C minus R. Okay, so where Cr and Cr minus is ion concentration, E is the electric charge. Okay, so plus minus, and A tilde is a Avogadro number. So for an arbitrary collection of ion with valence Z1, so let's say Na plus is Z1, Zi is plus, and concentration Ci, the charge density can be written as rho r. So this one can be written as I Zi Ci R. Okay, so kita banyak contohnya Na plus tu ada 100. So kita summarize or sum all the concentration and the charge at of that ion at this point, this R point. Okay, so we can do the summation. Okay, so the relation between concentration and potential energy using the Boltzmann equation, Boltzmann distribution. So we have this equation. So if we put this into this equation and then this equation into this equation, so we are going to get the Poisson-Boltzmann equation. Okay, so we have this delta U minus 45 E 80 delta 3 bar epsilon Zi Ci infinity exponential minus this energy. Okay, so the solution, so if we solve this equation, okay, so we solve this equation using the math method or advanced method. So we are going to get the electrical potential that take into account the screening of by ion. Okay, so we have this solution. Okay, so if this interaction weak, so this exponential is less than 1. So from our Taylor expansion, Ex equal to 1 plus x plus 1 over 2x squared plus 1 over 6x cubed. So this one can be written as 1 minus E Zi mu over kt. Okay, so if we put this into this equation back, so we are going to get the linearized Poisson-Boltzmann equation. So we have this equation. So where sigma I E Zi Ci infinity equal to 0, we have there is no ion at this that at infinity. Okay, so here we can see that rather than from using the exponential, so we have this just multiplication of this linear equation. Okay, so simplifying this equation, so we can have a Debye length, so where Debye length is the measure of a charge carrier net electrostatic effect in solution and how far those electrostatic effect persist. Okay, so sampai mana kalau ion tu, sampai mana dia punya influence kepada ion-ion di sekitar dia. Okay, so here simplifying this one, so we have 1 over lambda d squared equal to 8 pi exponential squared a to the 10 to the minus 3 I over 1 epsilon kt. So where I is ionic strength, so I is, we can see that we can use this 1 over 2, so we can get this equation. Okay, so using this equation or this Debye equation, so we can simplify the Poisson-Boltzmann equation as this equation. Okay, so here we can see that the the electrical potential for both sides. This is both electrical potential and this one also electrical potential. So we can use our math method or advanced method to solve this equation. Okay, so the example for 1 mole of NaCl, I equal to 1, T at 298 Kelvin. So lambda for the Debye length is 3.05 Armstrong. And for 1 millimole NaCl, 1 over 2 T 298 K lambda D equal to 30.5. Okay, so here we can see that for the I concentration, so the Debye length of the it will fill, or the other ion will fill it at near site 3.05. For the dilute salt, okay, so the Debye length for the it will fill after 30.5. Okay, so here what we can say is that lambda d is proportional to I square root of I, 1 over square root of I. Okay, so I small, the Debye length increase. Okay, the ionic strength, small ionic strength, so this Debye length increase. So what we can also say is that at distance shorter than a lambda d, electrostatic interaction will be strong. Okay, so Na plus, Na plus coming together, so we have the repulsion interaction, so electrostatic interaction will be strong. At longer distance, they will be evaporating out by the ion. Okay, so kalau Na plus jauh, so Na plus will not feel the effect of the other Na. So Debye length, we can say that as the ionic staining. Okay, so berapa jauh, berapa range that can the charged molecule or the charged protein will. Okay, but if I is proportional to Z squared, the multivalent ion, so let's say Na plus, K plus, so many ions in the solution, so the ionic strength increase, so the Debye will decrease. Okay, so let's see the activity for one. Okay, so here what we can say is that the ionic solution are not ideal. So kalau in 100 millimole NaCl to at osmolarity of 187 greater than 200. Okay, so kalau kita ada 200 100 molekul Na, 100 molekul atom Na plus and 100 molekul atom Cl minus, ion Cl minus, but in solution not all will dilute or solid in the solution. So here let's say these are 200, but we are supposed to have 200, but it is only 187 ions in the solution because these are just the attraction between the opposite side. Okay, so if we take the previous one, the linearized Poisson-Boltzmann equation in spherical coordinate, so we will replace nabla squared with this spherical coordinate, so we can write it as this one, and if we multiply by r and integrate, so we are going to get r with a exponential minus r lambda d plus exponential r lambda d. Okay, so and since b equal to 0, since the electrical potential at infinity is equal to 0, so the potential bar from the center, so can have the solution as E equal to the electric field of the surface of radius E equal to Q over X bar epsilon A squared, and associate with E R, so we have A exponential R lambda D over R, and if we set R equal to A, so we get a constant for this one, so this one B equal to 0, here we have A equal to Q A. So the solution here, so we putting A in this one and B equal to 0 into this equation, so we are going to get the electrical potential for the spherical coordinate is equal to this equation, or also equal to this equation. Okay, so this one is Coulombic interaction, and this one ionic trading. Okay, so if lambda d is greater, so here, so there will be no, there will be a small contribution from this ionic trading. Okay. Okay, so the work done by the ionic screening, this ionic screening, can equal to Q prime dQ prime, okay, 0 to Q from the electrostatic interaction. So when we integrate, so we have minus equal to, the work equal to minus Q squared over 2 bar epsilon 1 over lambda D plus A. Okay, lambda D is by length, and A is the sphere, the radius of the sphere. Okay, so the free energy equation, so when we have this ionic spinning, so G equal to D naught plus RT ln C plus W is work. So for activity coefficient sigma, so these are for a single ion, so we can have this is just like the entropy, okay? So W equal to KT ln gamma, so putting this equation into this equation, so we have ln gamma equal to minus this equation. So if the lowest concentration, so lambda D is greater than A, so the screening is greater than the spherical radius, so we can write this Deborah-Hackley law as this equation. Okay, so we can ignore this lambda lambda d is greater than A, so we can ignore A, so we only have lambda d. Okay, these are examples: 298 Kelvin, log 10, 0.96 C for monovalent, and minus 1.751 C for the divalent. Okay, so these are the the energy function. Okay. Okay, so we can refer in your figure 11.2. So that the limiting law work as long as the concentration is low. Okay, so if the concentration is low, then this T by Haeckel limiting law. Okay, and depend only on ion charge. Ion with the same number of charge will follow the same limiting law. Okay. Okay, so only ion charge, so meaning that if we have Na plus K plus uh, Na plus K plus, okay, for example, so all have the same number of charge, plus one, so we can summarize it, or we can simplify it for treat Na plus as K plus. Okay. Okay, so if lambda d not greater than A will affect the hydrogen cell that prevent the ion from getting too close. Okay, so this one is just like contohnya macam kita punya bumi, kita ada atmosfera. Okay, so sebelum contohnya sebelum asteroid kena ke bumi, dia akan melalui kita punya atmosfera. Okay, so that atmosphere is just like this hydrogen. Okay, the charge potential for the Poisson-Boltzmann equation. So putting back into this again the solution, so we can get this figure 11.3. Okay, so if we plot we play with this number, we change the R, A, the R, we fix the A, we fix the lambda D, Q. Okay, so we can see the distribution of the ion depend on the R. Okay, so the maximum charge density is R equal to lambda D from this equation. Okay, and for longer lambda D, the atmospheric cloud is more spread out. Okay, so we have this distribution of the ion. Okay, but we say that these are for the low concentration. So for the high concentration, so thereby Haeckel at higher concentration. Okay, so why? Because the region with the highest ionicity give us potential that is low enough for the ionization approximation to work. Okay, see, highest ionicity, so we cannot do the Taylor expansion for this higher concentration. Using potential based on the average charge density through R, the mean charge density does not give the correct weight to this multi-ion configuration. Okay, so we're going to have a very wrong answer. Okay, for if we are doing the curve fitting, so if we have a very different high error of for that curve fitting. So how to fix it? So these are from your EDA, I believe, or your from Statistical Physics 1 or 2. So